Welcome back. In this video, we are going to solve problem 4-100 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the rigid beam is supported by pin at A and 2 steel wires, each wire having diameter of 4 mm. If yield stress for the wire is 530 megapascal and modulus of plasticity of steel is 200 gigapascal, determine. The first part is intensity of distributed load W that can be placed on the beam that will cause only one of the wire to start yield. And in B part, smallest intensity of distributed load that will cause both wire to yield. For the calculation, assume that steel is elastic, perfectly plastic. So you can see this is the beam. Clear, there is a pin support at point A and at point B and C there are two steel wires of having diameter 4 mm. And there is a distributed load acting on over the whole length, which is W. So you have to find this W for one of the wire to yield, and then in second part we have to determine this W for both wires to yield. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having a vertical reaction force, and this will be RAY, as well as there is a horizontal reaction force which will be equal to RAX. And similarly, if you remove this wire BE, so there will be a vertical reaction offered by this wire EB or BE on the beam, and same is the case for wire CD, that it will act a vertical reaction force on beam which equal to FCD. And there is a distributed load of magnitude W. So when this distributed load is converted into a point load, so it will act at the middle of this beam, and the magnitude will be W into the length, and length is 400 plus 250 plus 150 is 800 millimeter, which will be equal to 0.8 meter, and its unit will be Newton per meter. Clear? Now we'll find this FBE and FCD by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, the first moment will be FBE, and perpendicular distance is 400, which is 0.4 meter, and it is producing counterclockwise, so it will be positive. So I will write FBE multiply by 0.4. The second moment that is produced due to FCD and perpendicular distance is 0.65 meter, and it is also producing counterclockwise movement, so it will be positive. So I will write plus 0.65 times FCD, and the last moment that is produced due to this load and perpendicular distance is 0.4 meter, and this is producing clockwise, so it will be negative. So I will write minus 0.8 W times 0.4 is equal to 0. So 0.4 times FBE plus 0.65 times FCD is equal to 0.32 times W, and this will be your equation number 1. Now from our observation, the wire CD will yield. So what we are going to do, we will find this force in CD due to yielding will be equal to yield stress into the area. So yield stress is given as 530 megapascal, so 530 into 10 to the power 6 multiplied by area. Since it is circular, so pi by 4 into D, which is 0.04 meter, and its square. That will give you FCD. So when you calculate this, FCD will be equal to 6.660 kilonewton. Now you have this value of FCD, so I will draw, let this was the initial beam. Clear? So this is your point A, this is your point B, this is your point C, and this is your point G. So due to this load, the beam will deflect like this. So this B point will come toward new point, which will be B dash. C point will move toward new point, which is C dash. So you can see we have the distance between A and B is given as 0.4 meter. From B to C, it is 0.250 meter. And from C to G, it is 0.150 meter. Clear? So we have, now you can see we have here, we will take two similar right triangle. One is this one, and another one is this one. So distance between B and B dash will be equal to delta B E, and from C to C dash it is delta CD. So by using this distance will be delta G. So by using similar triangle E, this is the triangle A B B dash and triangle AC C dash. So the ratio of their sides will remain same. So if we take delta BE divide by 0.4, so what I'm going to do is that I take this side and divide by this. The ratio of these two sides will give you delta BE divided by 0.4, and it will be equal to, if you take this right angle triangle. Clear? So delta CD divided by 0.65, delta CD divided by 0.65. So from here we will get delta CD will be equal to 1.625 times delta BC. Now we know that change in length is equal to force into length divided by A into E. So we will write this delta as FCD into LCD divided by area into E is equal to 1.625 times del BC will be equal to FBC into LBC divided by area into E. So again, you can see both lengths LCD and BE both are 800, so it will cut with this. Clear? Similarly, area will be same and modulus of elasticity is same. So what we will get is that FCD is equal to 1.625 times FBC. Clear? Now you have this equation. Let this equation is equation number 3. So put equation 3 in equation, put the value of this. Let this is your equation number 2. So put equation 2 in equation number 3. So when you put the value of FCD, so FBC will be equal to FCD divided by 1.625. So 6.660 divided by 1.25. 1.625 will give you FBC. So FBC will be equal to 4.009 kilonewton. And let this is your equation number 4. Now put the value of equation 2 and 4 in equation number 1. This is your equation number 1. So putting equation 2 and equation 4 in equation 1. So how we will put is that 0.4 times FBE. Okay, FBE. So this is delta BE. Okay, so this is BE, not this is same as this is not BC, this is BE. Clear? BE. So delta BE. So 0.4 FBE, so 4.009 plus 0.65 times FCD. So FCD is 6.660 is equal to 0.32 W. So from here, what we will get, W will be equal to 18.7 kilonewton per meter. So this is the value of distributed load for one wire to yield. Clear? Now we'll move toward our second part, and in second part, both wires yield. So if both wires yield, so FBE will be equal to FCD, and that will be yield stress into area. So what is the yield stress? That is 530 into 10 to the power 6 multiplied by area. So area of wire is pi by 4 into 0.004 square. So it will give you FBE is equal to FCD, and that will be equal to 6.660 kilonewton. Now put FBE and FCD in equation 1. Equation 1 is this one. Clear? This one is the equation 1. So when you put it, you will get W will be equal to 21.9 kilonewton per meter. And this is the value of distributed load for both wires to yield. And that is all about this problem 4-100. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-95 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the 10 mm diameter shank of steel bolt has a bronze sleeve bonded to it. The outer diameter of this sleeve is 20 mm. If yield stress for steel is 640 megapascal and for the bronze, this is 520 megapascal, determine the largest possible value of P that can be applied to the bolt. Assume the material is to be perfectly plastic. Elasticity of steel is 200 gigapascal, and for bronze it is 100 megapascal. So you can see this is bolt, clear, having diameter 10 millimeter, and that is sleeve, bronze sleeve, that is made up of bronze, that is bonded to it, having outer diameter 20 millimeter. So diameter of bolt is 10 millimeter, in meter it is 0.01. The outer diameter of sleeve is 20 millimeter, which is 0.02 meter, and inner diameter is same as for bolt. Sleeve is made up of bronze. Yield stress for steel is 640, while yield stress for bronze is 520 megapascal, and their modulus of elasticities are mentioned. So you have to determine the largest possible value of P that can be applied to the bolt. And how we will find this? So let's start with the solution. So first step is that what if I cut the bolt over here or any length and draw the free body diagram. So let me draw it, that this is the head of this bolt, clear, and this is the sleeve. This is the sleeve. Okay, and this is the dotted line is the diameter of this bolt. So when I cut it, so you can see at the top we have a load P, which we are going to find, clear, and you can see that this load is taken, some of this portion of this load is taken by this bolt, which is represented as PB, clear, PB, and some of this load is taken by the shank, so that is PS. So total load P will be equal to PB plus PS. So how we'll find this? By using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and force upward is taken as positive. So I can write P minus PB minus PS is equal to 0, or you can also write it that P is equal to PB plus PS. Clear? Now, how will find this PB and PS? And we are interested to find out the largest load. So I will write a statement that the largest possible P can be applied when you consider when P causes both bolt and sleeve to yield. That is the maximum load P that can be applied. So how we'll find this PB? So we know that yield stress for the steel is equal to load taken by the bolt divided by area of bolt. Clear? So from here, this PB will be equal to yield stress for the steel multiplied by area of bolt. So you can see 640 megapascal is the yield stress for steel. So 640 multiplied by 10 will be in pascal multiplied by area of bolt. Diameter is given as 10 millimeter, which is 0.01 millimeter. So area of bolt is pi by 4 d square, db square. So db is 0.01 square. That will give you PB. This PB will be the load that will cause the yielding in steel rod or steel bolt. And when you calculate it, you will get 50.265 kilonewton. Now we'll find the PS of sleeve. So we have yield strength for bronze that will be equal to P of brass. This is P of steel, PS. This is PS because this is the load taken by the steel. Now P of brass divided by area of brass, and similarly this will be AS, area of steel. So kindly make this correction. Okay, so from here, load taken by brass sleeve will be equal to yield strength of this brass multiplied by area of this brass. So the brass yield stress is 520 megapascal, so 520 multiplied by 10 to the power 6, and this sleeve having outer and inner diameter, so it will be equal to pi by 4. Outer diameter is 0.02 square minus inner diameter is 0.01, and the formula is pi by 4 d outer square minus d inner square. Now when you calculate it, the load taken by this brass sleeve will be equal to 122.52 kilonewton. As we know that we are interested to find of P, and we know that P is equal to PB plus P of steel, which we have written over here. Clear? So put the value 50.265 is the value of steel, load taken by this steel rod or bolt, plus P bronze, which is 122.52 kilonewton. So when you add them both, so you will get 173 kilonewton. So this is the maximum amount of load P that can be applied on this steel bolt having bronze sleeve bonded to it. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon for getting the upcoming videos. And if you have any question, you can ask me in comment section. Thank you for watching and keep supporting me like this. Welcome back. Problem 14-11. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy in A36 structural steel W10 by 12 beam. Obtain the answer using the coordinate x1 and x4 and then x2 and x3. So you can see this is the beam W10 by 12. At this point there is a pin support. At this point we have a roller support, and at this end we have 6 skips load. Clear? The total length of the beam is 18 feet. Clear? So from the table mechanical property for A36 steel, E is 29 into 10 to the power 3 KSI, and from wide flange section table, I moment of inertia for this is 53.8 inch power 4 for this beam. I will show you it later. So we have to determine the bending strain energy using x1 and x4 and x2 and x3. So let's start with the solution. So what will be the first step is that if you remove this pin support, so you'll be having reaction force. Let this is your point A and this is your point B. So the vertical reaction, and there will be horizontal reaction. Clear? So if you remove this roller support, so you'll be having reaction force that will be upward. Why upward? Because you can see 6 skips is downward, so this will be upward. Let this is RB, and this vertical reaction force at RA will be downward. So this is RAY, and this will be equal to RAX. So you will find this RAX, RAY, and RB by using equation of equilibrium. So what will be the equation of equilibrium? So first equation of equilibrium is that sum of all movement about point A is equal to 0, and taking the counterclockwise movement as positive. So you can see this length is 12 feet. So in inch it will be 12 by 12 inch. Clear? That will be equal to 144 inch. Clear? And this 6 feet will be equal to 6 multiplied by 12, which is equal to 72 inch. Okay. So sum of all movement about point A is equal to 0. So first movement will be this RB into perpendicular distance is this one, and this is producing counterclockwise movement, so it will be positive. So I will write RB multiplied by 12 multiplied by 12. Clear? The second moment is due to this 6 kips load and the perpendicular distance is 18 feet. So I will write 18 multiplied by 12, that will be converted into inch, and this is producing clockwise movement, so it will be negative. So I will write minus 6 multiplied by 18 multiplied by 12 is equal to 0. So from here, this 12 multiplied by 12 times RB is equal to 6 into 18 multiplied by 12. Okay, so this 12 RB will be equal to 6 multiplied by 18. So from here, you will get RB is equal to 6 multiplied by 18 divided by 12, and you will get this RB will be equal to 9 kips. Clear? Okay. This will be RBY because this is the vertical component. Okay. So RBY is 9 kips. Now we'll find this RAX by using this equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force toward right direction is positive. So there is only horizontal force RAX, there is no other force, so it means that RAX will be equal to 0. Now we'll find this RB by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So from here, RAY which is equal to, which is not known, so RAY which is minus, clear? Okay. So RAY which is minus plus RBY which is 9 kips minus 6 is equal to 0. So it means that RAY is equal to 3 kips. Okay. Now you have all these reaction forces. So we will move toward finding bending strain energy. And we know that bending strain energy is equal to integral of m square dx over 2EI, and it is from 0 to length L. So what we are going to do is that first we will solve this by using x1 and x4 coordinate. So for x1 we will cut the beam over here and we will draw the free body diagram. So for x1 coordinate, I cut the beam and draw the free body diagram. Here you can see you have RAY which is 3 kips. Clear? This coordinate is having length x1, and when you cut it you will be having a shear force V1 and there will be a bending moment M1. That this is your point 1. Now applying equation of equilibrium, that sum of all moment about point 1 is equal to 0, taking the counterclockwise moment as positive. So we will need this bending moment because we will use it in this equation. So 3 into perpendicular distance about point 1 is x1, and this is the moment which is positive. So 3x1 plus m1 is equal to 0. So from here we will get m1 is equal to minus 3x1. This is the moment equation for coordinate x1. Now what we will do is that we will do for coordinate x4, because in first part we have been given for x4. So x4 is this one. So we will cut the beam over here and take the right side in order to draw the free body diagram. So I will draw the free body diagram. It will be like this. You can see at this end we have 6 kip load. This is x4. Clear? So when you cut it, you will be having shear force upward. Here this is V4 and there will be a moment M4. Let this is point 4. So how we will find this M4? By using equation of equilibrium, that sum of all moment about point M4 is equal to 0 and taking the counterclockwise moment as positive. So this force 6 into x force is producing moment about point 4, that is clockwise, so it will be minus 6x4. So minus 6x4 plus minus this M4 is equal to 0. So from here you will get M4 is also equal to minus 6x4. Now you have both the moments. So what we are going to do, we will put it in this formula. So let's put it. So we know that strain energy due to bending moment is equal to, for coordinate x1, you can see its length from 0 to 144 inch. For x coordinate 1, x1 0 to 144 inch. Clear? And for x4, it is from 0 to 72 inch. So we will put the value of m1. M1 is minus 3x1 square into dx divided by 2EI. Plus integral of from 0 to 72, and m4 is minus 6x4 whole square dx divided by 2EI. Now what you can do is that you can take 1 over 2EI common because they are constant. So we're left with integral of 0 to 144 minus 3x1 square dx plus integral of plus 1 over 2EI into integral of 0 to 72 minus 64x4 square into dx. Not minus 64, minus 6x4. Okay, so this will give us 1 over 2EI, and that we will get 9x1 square integral of 0 to 144 dx plus 1 over 2EI integral of 0 to 72 36x4 square into dx, and that we will get 9 over 2EI integral of x1 square will be equal to x1 cube over 3 and limit will be from 0 to 144. Similarly, 36 over 2 EI and integral of x4 power square will be x cube 4 over 3 and integral from 0 to 72. So at the end, when you calculate it, and you can put the value 9 over 2 EI into 144 cube over 3 plus 36 over 2 EI into 72 cube over 3. Now you have the value of E and I. So 2 divided by E is 29 into 10 raised to the power 3 KSI. I is given as from the table 53.8 multiplied by 144 cube over 3 plus 36 over 2 times 29 into 10 raised to the power 3 divided by multiplied by 53.8 into 72 cube over 3. That will give you strain energy due to bending for coordinate x1 and x4. So when you solve this UI strain energy due to bending moment, that comes out to be 4.31 kips into inch, which is the answer of our first part. Welcome back. Problem 3-21. This problem is taken from chapter number 3, Mechanical Properties of Materials, and book name is Mechanics of Material by R.C. Hibbeler. Statement is the two bars are made of polystyrene, which has the stress strain diagram shown. If the cross-sectional area of bar AB is 1.5 square inch and BC is 4 square inch, determine the largest force P that can be supported before any member ruptures. Assume the buckling does not occur. So you can see these are two bars. This is bar BC and this is bar AB. At this point we have pin supported and C is also pin supported. Here we have a P load. The stress strain diagram for this two bars are given. For the tension, for member tension, this will be the stress strain curve, and for the member which are in compression will be follow this stress strain curve. So you have to find the largest load P that can be applied before any member rupture. So let's start with the solution. So what will be the first step is that we will use method of joint at B in order to find the forces in CB and AB. You can see due to this load P, clear, this bar CB will be in tension and this AB will in compression, clear. So while taking the method of joint at B, so this bar CB will exert a force on B at this direction. Similarly, the bar AB will exert a force on at point B in this direction. So let me draw the free body diagram. This is point B, clear, where we have a load P that is acting downward. Clear. The force that member CB exert on point B will be this FCB, and the load that this member AB act on point B will be this one, and this is an inclined force. This is FAB. Now you can see the ratio of their side. This is 3 feet, this is 5 feet. So horizontal will be 3 feet, vertical will be horizontal is 4 feet and vertical is 3 feet. So this hypotenuse will be 5 feet, and we can find its horizontal and vertical component by using equation of equilibrium. So what will be the first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So one force, which is P, is acting downward, so minus P plus the vertical component of this force. So it have two force, one is this, another one is this. So this component will be, if you take this is theta, clear. So let this is theta. So what will be sine theta? So sine theta will be equal to 3 over 5. And what will be cos theta? So cos theta is equal to 4 over 5 base by hypotenuse. So vertical component will be FAB sine theta will be equal to 0. So minus P plus FAB and sine theta is equal to 3 over 5 is equal to 0. So it means that 3 over 5 FAB is equal to P. And from here we will get FAB will be equal to 1.6667 times P. Now we apply another equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So FCB is acting in opposite direction. So I will write FBC, clear. The horizontal component of this will be like this, and this will be equal to FAB cos of theta. So let me write it plus FAB cos of theta is 4 by 5, clear, is equal to 0. So from here you will get FBC is equal to 4 over 5 time FAB. Now you know that FAB is 1.6667 times P. So you can put the value, and at the end you will get this FBC, and FBC will comes out to be 1.333 times P. Now you have both FAB and FBC. So what we will do is that we will first assuming failure of bar BC. From this figure, you can see that due to this load, the bar BC will be in tension. So you will use this stress strain diagram. So from this stress strain diagram, rupture stress due to tensile loads comes out to be 5, clear. So we can write 5 KSI. we know that stress is equal to force per unit area. So for this member BC, we will have rupture due to tension will be equal to FBC divided by area of BC. So what we have is 5 KSI is equal to FBC divided by area of BC is 4 square inch. So 4. So from here you will get this FBC will be equal to 20 kips. Now you have this FBC is 20 kips. So you can see you can put it in this equation. So what you will get is that 20 is equal to 1.333 times P. So what you will get is that P load due to this member BC, and this P loads comes out to be 15 kips. So this is one load that is due to the member BC. Now what we will do is that we will use assuming failure of bar BC, AB. You can see that due to this load, this bar AB is in compression, clear? So we will use this rupture stress due to compression. So I will write rupture due to compression is equal to 25 KSI from stress strain diagram, and this rupture due to compression is equal to FAB divided by area of AB. So from here FAB will be equal to rupture due to compression into area of AB. So you have both the value 25 multiplied by area of AB is 1.5 square inch. So 1.5, and you will get this force in member AB. So this force in member AB comes out to be 37.5 K. Now this is the force FAB. So you can just put it in this equation. FAB is 1.66 times. FAB is equal to 1.6667 times P. So from here P will be equal to FAB divided by 1.6667. So put the value 37.5 divided by 1.6667, and you will get this P will be equal to 22.5 kips. So this is the load P that is due to member AB. Now we have two values. One is this one, another one is this one. So we will choose the largest load. We will choose the largest load that can be applied on this system will be P will be equal to 15 kips, because this will be the safer load. So we will choose smaller one, and that is the largest load that can be applied on the system. So this was all about this problem 3-21. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-89 that is taken from chapter number 1, stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the required minimum thickness T of the member AB and edge distance B of the frame if P is 9 kips and the factor of safety against failure is 2. The wood has a normal failure stress 6 KSI and shear failure stress of 1.5 KSI. So you can see this is the member AB and the thickness is not known. We have to find this thickness and this B distance. The load acting or this frame is P, which is 9 kips. The normal failure stress is 6 KSI and shear failure stress is 1.5 KSI. So you have to determine this thickness T and this B of the frame. So let's start with the solution. So first we will find internal loading. So let me write it first. The normal force developed in member AB can be determined by considering the equilibrium at joint A. So what we will do is that we will take this joint A and we will draw the free body diagram and we will find the force AB. So let me take this. This is member AB and this is member AC. Here. Okay. So this is member AC and this is member AB. This is B. This is your point A and this is your point C. At A we have vertical load of P, which is given as 9 kips. So 9 kip. So when you cut it, section B, so you'll be having a reaction force acting on section AB. Let this force is FAB, and when you cut it, you will be having a normal force, normal axial force, which will be equal to FAC. Now, if I take a horizontal line from this, so it will be, let this will be your x-axis and this will be your vertical will be your y-axis. And you can see here, this makes an angle of 30 degree. So again, if I draw horizontal line, so this will be also 30 degree. So it's called alternate angle. So this angle will be 30 degree. Here, this angle is also 30 degree. Now, if I take the center line of this member and this member, so we will apply equation of equilibrium in order to find the FAB and FAC. So this FAB will have two component. This FAB will have two component, one along x-axis and other along y-axis. Clear? So we will apply equation of equilibrium that sum of all forces along x direction must be equal to 0 and upward force is taken as positive. So you can see this force will have one component. This FAB is like this. So it will have one component this and other. So horizontal component will be equal to FAB cos of 30 degree. And since it is toward positive side, so I will write it FAB cos of 30 degree. And same is the case, this FAC will have two component. One is this one, another one is this one. And this component is FAC cos of 30 degree. And it is toward negative direction. So I will write minus FAC cos of 30 degree. And their sum must be equal to 0. So it means that FAB cos of 30 degree is equal to FAC cos of 30 degree. So cos of 30 will cancel each other. So FAB will become equal to FAC. Okay, now we'll apply another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is downward is -9. So I will write -9. This component, the vertical component of this force, which was FAB sine of 30 degree is upward, and similarly FAC sine of 30 degree is also upward. Their sum must be equal to 0. So plus FAB sine of 30 degree plus FAC sine of 30 degree is equal to 0. Now you can see FAC is equal to FAB. So I will replace this FAC with FAB. So it will be FAB sine of 30 degree plus FAB sine of 30 degree minus 9. So 2 times FAB sine of 30 degree is equal to 9. And when you divide it, FAB will be equal to 9 divided by 2 sine of 30 degree. So you will get FAB will be equal to 9 kip. Clear? So let me write it. FAB is equal to FAC is equal to 9 kip. Now we have this force in member AB and AC. So what we are going to do is that you can see that this member is over here. So due to this force FAB, it will be having two components, one along x-axis, y-axis, and another along x-axis. So this force will cause the shearing in this region, So we'll find that. So let me draw its free body diagram. So I will write, if I take that portion, or if I take the member AB and joint B using joint B of member AB. So this is joint B. Clear? So you can see you will be having this FAB in this direction. FAB will be like this. This is FAB. So it will be having two components. One is this one and other one is this one. Clear? This is angle 30 degree. So this component will be equal to FAB cos of 30 degree, and this component will be FAB sine of 30 degree. So we'll find this FAB cos 30. So what I am going to say is that this is the member AB. Clear? And this was the joint like this. This is the member. So force in this member was 9 kip. And it will having two components. This is 30 degree. Clear? And this is your point B. So at point B, you can check it that it will have a reaction force in horizontal as well as in vertical direction. So I will write this horizontal component will be FBX and the vertical component will be FBY. Now, what we are going to do is that we will find this FBX and FBY by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see we will need only this horizontal reaction force because it is creating shear at this point. Clear? At this point. So we'll find this by using equation of equilibrium which I have written. So FBX minus the horizontal component of this, which is 9 cos of 30 degree. So I will write it minus 9 cos of 30 degree is equal to 0. So from here FBX component will be equal to 7.794 kip. Now this horizontal force is actually, you can see it will exert by this member over here. As a result, this member, this force, horizontal force, will produce shear in this area. So if I draw a free body diagram of that portion, so that this is the portion where you have a net force of FBX. FBX is applied, and due to that we have a shear V, which is taken as VA dash A. What is A dash A? So let me show you that. If you take this line, so this is the plane AA where you cut it, and we have drawn the free body diagram over here. Okay, so FBX is 7.794 kips. So by using equation of equilibrium, sum of all forces along x direction must be equal to 0, and force in this direction is positive. So VAA minus 7.794 is equal to 0. So VAA means shear force, horizontal shear force, will be also equal to 7.794 kip. Now you have both this normal force in member AB and shear force. So what we are going to do is that we will find the allowable stresses. So let me write it: allowable normal stress and shear stress. How we'll find that? We have been given this normal failure stress and shear stress. We also know the factor of safety. So using these values, we will first calculate allowable shearing stress. So allowable normal stress. So allowable normal stress is equal to failure stress divided by factor of safety. Clear? So failure stress is 6 and factor of safety is 2. So it means that allowable normal stress is 3 ksi, and same is allowable shear stress is equal to failing shear stress divided by factor of safety. So failing shearing stress is 1.5 divided by 2 is 0.75 ksi. So now we will use these two to find the force in AB, and we will find the distance B. So first we know that allowable normal stress is in member AB is FAB divided by area of AB, that is equal to 3 into 10 to the power 3, and FAB is 9 ksi. So I will write it 9 into 10 to the power 3. Now what is area of AB? So you can see the thickness is this one, which is not known, and the width is 3. So it's actually T by 3 inch. So we will use this. Area is 3 multiplied by T. Clear? So from here you will get T will be equal to 9 into 10 to the power 3 divided by 3 into 3 multiplied by 3, which is equal to 1 inch. So this is the answer of our first part. Now we'll find this tie allowable is given as VAA divided by area of AA. So let me show you. You can see here shear stress is VAA and the area is this B. Clear? And the area is B multiplied by this thickness. You can see this is 3. Sorry, this is, so this is the length B and this is the width 3 inch, and this will be the shading area. So it will be 3B. So put the values. VAA is 7.794 divided by 3B is equal to allowable shearing stress, which is 0.75 into 10 to the power 3. So what we will get is that B is equal to 7.794, and there is 10 to the power 3 because K is pound kip. So 10 to the power 3 divided by 3 into 0.75 into 10 to the power 3. So what you will get is B is equal to 3.46 inch. So that is the answer of our second part. So I will conclude that this thickness T is equal to 1 inch and this B is equal to 3.46 inch, which is the answer of this question. And that was all about this problem 1-89. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 1-86. This problem is taken from chapter number 1, Stress, and book name is Mechanics of Material by R.C. Hebler. So statement is the two aluminum rods supports the vertical force of 20 kilonewton. Determine their required diameters if allowable tensile stress for the aluminum is 150 megapascal. So you can see this is rod AB and this is rod AC that is acted upon by a 20 kilonewton load acts downwards. So due to this load, there will be a tensile stress in rod AB as well as in AC. And this rod AB makes an angle of 45 degrees with the horizontal. So you have to find the diameter of rod AB as well as diameter of rod AC. So let's start with the solution. So first step is that we will take this point A and we will draw the free body diagram. So P is acting downward. So this rod exert a force in this direction on point A, as well as this rod exert a force in this direction, which is FAC and this is FAB. Clear? So we will draw the free body diagram. Free body diagram. So let this is your point A. Clear? This is A. So at A we have P, which is acting downward. This is rod, force in rod. The rod AB exert a force FAB at point A, and this makes an angle of 45 degree. Similarly, this rod AC will exert a force in this direction, FAC. Clear? And this is your point A. So we'll apply equation of equilibrium. So the first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see FAB will have two components. One component will be along x direction. Clear? One is x component. Clear? Which is FAB cos of 45 degree, and one will be its y component, which will be the vertical component, and this component will be FAB sine of 45 degree. So you can see one component which is FAB sine of 45 degree. Clear? And this P, which is 20 kilonewton, that is acting downward. Their sum must be equal to 0. So I will write minus 20 is equal to 0. So FAB will be equal to 20 divided by sine of 45 degree. And when you calculate this force, so force exerted by member AB at point A will be equal to 28.284 kilo Newton. Now we will find this FAC by using equation of equilibrium, that sum of all forces in an x direction must be equal to 0 and force in this direction is taken as positive. So FAC is in opposite direction, so I will write minus FAC, and this component FAB cos of 45 degrees in positive direction, so FAB cos of 45 degree is equal to 0. So FAC will be equal to FAB cos of 45 degrees. So FAB is 28.28 into cos of 45 degree. And when you calculate it, you will get this force offered by member AC at point A will be equal to 20 kilonewton. 20 kilonewton. Now these are the forces that is acted upon by this member on point A, and this member, this exert a force in this direction and this exert force in this direction. As a result, due to Newton's third law, due to this load P, it will cause the tensile stresses in these rods. So we will find this. We have been given that stress. We know that stress is equal to force per unit area. Clear? So we have been given allowable tensile stress. Allowable tensile stress is equal to force per unit area. So what we will do is that for rod AB, we have allowable stress is equal to FAB divided by area of rod AB. So we have allowable stress, which is 150 megapascal. So 150 into 10 to the power 6 is equal to FAB, which is 28.28 kilonewton. So kilo is converted into Newton, divided by, this is circular rod, so its area will be pi by 4 DAB square. So pi by 4 DAB square. So from here you will get DAB square is equal to 28.28 into 10 to the power 3 divided by pi by 4 into 150 multiplied by 10 to the power 6. And if you take square root on both sides, clear, so you will get diameter of rod AB will be equal to 0.0155 meter. And in millimeter, the diameter of rod AB will be equal to 15.5 millimeter. Sorry. Now we'll find for rod AC. So for rod AC, we have allowable tensile stress is equal to FAC divided by area of AC. So FAC is 20 kilonewton. So 20 into 10 to the power 3 divided by area is pi by 4. We are interested to find out diameter, so DAC square. Allowable stress is 150 megapascal. So 150 into 10 to the power 6 is equal to 20 into 10 to the power 3 divided by pi by 4 into DAC square. So from here, DAC square will be equal to 20 multiplied by 10 to the power 3 divided by pi by 4 multiplied by 150 into 10 to the power 6. And if you take square root on both sides, so you will get diameter of rod AC will be equal to 0.0130 meter, which is equal to 13 millimeter. And that is the answers of this question. So diameter of rod AB is 15.5, while diameter of rod AC is 13 millimeter for the above given load. And that was all about this problem 1-86. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-84. This problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by R.C. Hibbeler. Statement is the frame is subjected to load of 4 kilonewton which act on member ABD at D. Determine the required diameter of pins at D and C if allowable shear stress for material is 40 megapascal. Pin C is subjected to double shear, whereas pin D is subjected to single shear. So you can see this is the frame, clear, that is acted upon by 4 kilonewton load at point D on this member ABD only, clear. So this, given that this C, there is a pin which is acted upon by double shear, and at point D the pin will have a single shear. So you have to determine the diameter of pin at D and C. So let's start with the solution. What we will do is that we will take this member ECD and we will draw the free body diagram. So first let me draw it first. So this is the member, clear. There is a point C over here, and at this point we have point D, clear. And you can see there is a roller support at point E. So when you remove it, so you'll be having reaction force which will be in upward direction. Let this is NE, clear. This is your point E and this is your point D, and there is a pin support at point D, clear. So when you remove it, so you will be having a reaction force, along horizontal. Let it be like this. This is dx, and you will be having a vertical reaction force which is taken upward, and let this is dy. At this point is point C. So you can see at C there is a member. So if you remove this member, so you'll be having a force which will be equal to FBC, and this FBC makes an angle theta with this horizontal. So what we will do is that we will find this theta. Distance between this E and C is 1 meter, clear, and distance between from C to D is 1.5 meter. Okay. Also, if you look at this figure, so this is 1.5 and this is 1.5, and this is the theta angle. So this theta will be equal to, if you take, let this is theta angle. So if you take tangent of theta, so this tangent of theta will be equal to perpendicular, which is 1.5 divided by base, which is 1.5. Clear? So theta is equal to tangent inverse 1, which is equal to 45 degree. So this theta is equal to 45 degree. Now we'll apply equation of equilibrium in order to find the dx, dy, and this FBC, because here you can see you have these pins at point C and D. So what will be the equation of equilibrium? So we will, first equation of equilibrium is that sum of all moment about point E is equal to 0, and taking the counterclockwise moment as positive. So about point E, the first moment will be this dy, and perpendicular distance is 1.5 plus 1, 2.5, clear? And this is 2.5 meter, and this is producing counterclockwise moment, so it will be positive. So I will write dy into 2.5. Now you can see this FBC will have two components, one along x-axis, one along horizontal, clear, this component. If you resolve it into its rectangular component, and other one will be a vertical component. So this component will be equal to FBC sine of 45 degree, and this component will be FBC cos of 45 degree. Since this horizontal component is passing through point E, it is not producing moment, so only vertical force is producing moment, and this force into perpendicular distance is 1, and this is producing clockwise moment, so it will be negative. So I will write minus FBC sine of 45 degree is equal to 0. Perpendicular distance is 1, so I will also write multiply by 1 is equal to 0. So from here you will get 2.5 times dy is equal to minus sine of 45 is 0.707, so 0.707 FBC. That this is equal to 0, and that this equation is equation number 1. Now we'll apply another equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see one force is this one, which is FBC cos 45 degree, and second is this one. Their sum must be equal to 0. So I will write FBC cos of 45 degree minus dx is equal to 0. So from here, cos of 45 is 0.707 FBC minus dx will be equal to 0, and then this is your equation number 2. Now what we will do is that we will take the free body diagram of this ABD member. So let me write it. Take member ABD and draw its free body diagram. So remember this ABD, so I will draw it over here. So let this is your vertical member here. This is your point D, where you have horizontal dx, clear. You have vertical component which is dy. Let me draw it by using another color. This is your dy, clear. And at point D, it was also given that 4 kilonewton load is applied on member ABD. So let it makes this 4 kilonewton is this one. This is 4 kilonewton, and it is making an angle of 45 degree, that is given. And this is your point A, clear? This is at end your point A, and you have pin support, so you will be having a vertical reaction force, and this is represented as AY, as well as you will have a horizontal force which will be equal to AX. And at point B, this is your point B. So at point B, you can see you have member CB, which force here is shown FBC is downward. So according to Newton's first law, this will apply force in this direction. The magnitude will remain same. So FBC will be in this direction. Okay, this is FBC, and this angle is 45 degree. This is 45 degree. So if you look at, so distance between D and B is 1.5, and this is also 1.5. So this distance is 1.5 meter, and this distance is also from B to A is also 1.5. So we will apply now equation of equilibrium in order to find this dx and dy. So what will be the equation of equilibrium? So we will apply the first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. Okay, so what we are going is that you can see you have this FBC, it will have two component. One will be this component will be FBC cos of 45 degree, and one will be the vertical component, which will be equal to FBC sine of 45 degree. Similarly, this 4 kilonewton will have two component, one along x-axis, which will be equal to 4 cos of 45 degree, and one will be the vertical component, clear? Which will be, this vertical component will be 4 sine of 45 degree. Okay. Now applying this equation of equilibrium, so this vertical component which is passing through point 8 is not producing movement. These two forces are not producing movement because they are passing through it. So one component which is producing movement is dx, clear? The other one is 4 cos of 45, and third one is this FBC cos of 45. This component will produce movement. So I will start from this 4 into cos of 45, and perpendicular distance is 1.5 plus 1.5, and it is producing counterclockwise movement, so it will be positive. So 4 into cos of 45 multiplied by 3. So I will write 4 into cos of 45 degree multiplied by 3. The second force that is producing movement is this FBC cos of 45, and perpendicular distance is 1.5, and this is also producing counterclockwise, so it will be plus. So plus FBC cos of 45 degree, cos of 45 degree, clear, into perpendicular distance is 1.5. The third moment is due to this dx, and this dx into perpendicular distance is 3, and this is producing counterclockwise moment, clear? So it will be also positive. You can see here. Okay, so one thing you have to make correction. You can see here at point D you have taken dx in this direction for members ECD. So this, on this member, this dx will be in opposite direction. So I will have to change this direction only. This dx will be in this direction. So this dx into perpendicular distance is this, and this is producing clockwise movement, so it will be negative. So I will write it minus dx into 3 is equal to 0. So now you can see this 4 cos of 45 multiplied 3 will give you 8.4852, plus this cos of 45 multiplied by 1.5 will give you 1.060, and there will be FBC minus 3 dx is equal to 0. Divide this equation by 3 to get dx, clear? So when you divide this by 3, so you will get 2.83 plus the second term will give you 0.35 FBC minus dx will be equal to 0. So from here you will get this dx will be equal to 2.83 plus 0.35 FBC. Let this is your equation number 3. So now what we will do is that put equation 3 in equation number 2. This is your equation number 2. You can see this is equation number 2. So 0.707 FBC minus 2.85 minus 0.35 FBC is equal to 0. So 0.707 BC minus this will give you 0.357 FBC is equal to 2.85. Okay, 2.85. So from here you will get this FBC will be equal to 8 kilonewton. 8 kilonewton. Now you have this FBC. So put value of FBC in equation number 1 and 2, clear, to get dx and dy. So you can see this is, you have to put the value of FBC over here and here, so you will get this dx and dy. So we for FBC is equal to 8 kilonewton in equation number 1. What is equation number 1? You can check it. Equation number 1 is this one. Clear? This one is equation number 1. So when you put it, you will get dy will be equal to 2.263 kilonewton, and for FBC is equal to 8 kilonewton in equation number 2. You will get dx, and dx is 5.63 kilonewton. Now you can see dx and this is dx and this is dy. These are the two components, clear, and their net effect will be acting on this will act on this point D, and we will find this. You can see if I take it like this and this, so its net effect will be like this. So net will be like this. So we will find this by using Pythagoras theorem. So let me find that. Thus, force acting on pin D is this FD, and that FD will be equal to dx square plus dy square under the root. So put the value 5.657 square, or this 5.63. You can take that plus 2.263 square under the root. So this FD will comes out to be 6.093 kilonewton. Now you can see that the net force acting on point D is FD, and this FBC is also there. So what we are going to do is that I will move to the next page. So first I will write, it is given that pin C is subjected to double shear. So if I draw this pin like this, clear? So this FBC was like this. This is FBC, which is 8 kilonewton. Let me show you over here. This is FBC, that is acting FBC, and that was 8 kilonewton. Let me show, this is 8 kilonewton. So for double shear, it will be, the shearing will be like this, VC and VC. It is given this is double shear, so this 2 times VC is equal to FBC, clear? So this shear force, single shear, will be equal to FBC divided by 2. So 8 divided by 2 will give you 4 kilonewton, clear? And pin at D is subjected to single shear, that is given. So what does it mean? It means that if you have pin like this, this is straight, clear? So if net force acting at point D, which we have calculated, is FD, and that FD was 6.093 kilonewton. So single shear, so it will shear on one side. This will be VD. So here VD is equal to FD for single shear, clear? I will divide it by 2. Okay. Now we have been given that allowable shearing stress, and we know that it is equal to V shear force divided by shearing area, clear? So for C, for pin C, this allowable shearing stress is equal to shearing force at C divided by shearing area at C. So VC is 4 kilonewton, clear? So 4 into 10 to the power 3 divided by shearing area. So shearing area is the area of pin is pi by 4 dc square, clear? And that is equal to allowable shearing. And allowable shearing stress is given as 40 megapascal. Let me check it. 40 megapascal. So 40 into 10 to the power 6 is equal to 4 into 10 to the power 3 divided by pi by 4 dc square. So from here, this dc square is equal to 4 multiplied by 10 to the power 3 divided by pi by 4 into 40 multiplied by 10 to the power 6. And if you take square root on both sides, so you will get that dc diameter of pin at C will be equal to 0.01128 meter, or in millimeter it will be equal to 11.3 millimeter. Now we'll find this diameter at pin D. So what we will go do is that allowable shearing stress is equal to VD divided by AD. So VD is 6.093 kilonewton divided by area, which is pi by 4 DD square. So from here you will get this DD square is equal to 6.093 into 10 to the power 3 divided by pi by 4, and tie allowable is 40 megapascal. So if you take square root on both sides, so you will get diameter of pin at D will be equal to 0.01393 meter, or in millimeter it will be equal to 13.9 millimeter, which is the answer of our this question. And that was all about this problem 1-84. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back to another episode that is about problem number 14-22. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement of this problem is determine the bending strain energy in the beam and the axial strain energy in each of two posts. All the members are made up of aluminum having a square cross section 50 mm by 50 mm. Assume the post only support vertical axial load. Modulus of elasticity of aluminum is 70 GPa. So you can see this is the beam and the loading is shown. There is a distributed load of 8 kN per meter, and there are two vertical posts that support this beam. So you have to find the bending strain energy in this beam and axial strain energy in this vertical post. So this vertical post offer only vertical reaction. So let's start with the solution. So what if we remove this post, two posts? So this will apply a vertical reaction on this beam. Let this is the beam. You can see this is the load that due to this post. So this is P of that this the load that this post apply on the beam is P of post, and similarly on other side the same length or same material post is applying a load P of post on this beam. There is a uniformly distributed load on this beam which is given as 8 kilonewton per meter there, and this load is downward. So we will find this P of post by using equation of equilibrium. So what will be the equation of equilibrium? So first step is that we will convert this distributed load into a point load. So this will be equal to 8 kilonewton per meter multiplied by the length, and the total length of this beam is given as 3 meter. So I will multiply it with 3. So this 3 meter. So this will give you 24 kilonewton load, and that will act at a distance of 3 divided by 2, which is 1.5 meter from either side. Clear? Okay. Now we will apply equation of equilibrium. So you can see the sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So P of post plus P of post. P of post is the load that this post apply on this beam. Minus 24 is equal to 0. So 2 times P of post is equal to 24. So it means that P of each post apply a 12 kilonewton load on this beam. Clear? Now we will move further, and what we will do is that we will cut this beam at any length x. Clear? And we will draw the free body diagram in order to find the equation for movement. So look, you can see this is the beam. Here we have one load P of post, which is equal to 12 into 10 to the power 3 Newton. Clear? And this total length of the beam where we cut it is x. And there is a uniformly distributed load on this, which is 8 kilonewton per meter. So when you cut it, you will be having a shear force and you will be having a moment. This is your point 1. So what we will do is that we will convert first this distributed load into a point load. So this will be equal to 8 multiplied by 8 kilonewton. So 8 into 10 to the power 3 multiplied by this length x, for which it acts. And this will act at a distance of x by 2 from either side. So this distance will be x by 2. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about point 1, one moment is this reaction moment, which is counterclockwise, and that will be plus. The second moment will be due to this 8 into 10 to the power 3 into x, and the perpendicular distance is x by 2, and this is also counterclockwise, so it will be positive. So plus 8 into 10 to the power 3x multiplied by x by 2. And the last moment that is produced due to this load and perpendicular distance is x, and this is producing clockwise, so it will be negative. So I will write minus 12 into 10 to the power 3x is equal to 0. So what I will get is m plus 4 into 10 to the power 3x square minus 12 into 10 to the power 3x is equal to 0. So if you further simplify it, this moment will be equal to 12 into 10 to the power 3x minus 4 into 10 to the power 3x square, and its unit will be Newton into meter. Okay, now this is the equation of movement. So we will move toward finding the bending strain energy due to bending, and we know that this is equal to integral from 0 to L m square dx divided by 2EI. Okay, so put the value integral 0 to L m square is 12 into 10 to the power 3x minus 4 into 10 to the power 3x square whole square into dx divided by 2EI. That is strain energy due to bending. Okay, now if you take this 1 over 2EI out of this integral, because these are constant, so you will left with 0 to L. So 12 into 10 to the power 3 square will be 144 into 10 to the power 6 x square minus plus 4 into 10 to the power 6 10 to the power 3 will be 16 into 10 to the power 6 x power 4 minus 2 times this term multiplied by this term will give you, I will directly write it, this will give you minus 96 into 10 to the power 6 x cube into dx. That will be equal to strain energy due to bending. Okay, again this bending strain energy will be equal to 1 over 2EI, and what we will take is integral. So 144 into 10 to the power 6 x cube over 3, and limit will be from 0 to L, plus 16 into 10 to the power 6 x5 divided by 5, and limit from 0 to L, minus 96 into 10 to the power 6 into x power 4 divided by 4, and limit from 0 to L. Okay, and you can see x start from 0 to x is equal to L, 3 meter. not L3. Total length is 3. So what is that? I will remove this L and I will write it 3. Okay, now we will find E of steel is given as 70 gigapascal, and it is given that this is square cross section 50 by 50. So the square cross section is this one. This is 50 millimeter, and the height is also 50 millimeter. Clear? So moment of inertia is equal to 1 over 12 BH cube. So 1 over 12, that is 50, and millimeter in meter it is 0.05, and height is also 50, which is 0.05 meter whole cube. So when you calculate it, you will get 0.52083 into 10 to the power minus 6 meter power 4. Now you have all the values, so you can just put it 1 over 2 multiplied by E is 70 gigapascal, 70 into 10 to the power 9 multiplied by 0.520 into 10 to the power minus 6 multiplied by all these values. 144 into 10 to the power 6 divided by 3x cube plus 16 into 10 to the power 6x 5 divided by 5. Limit will be from 0 to 3. Here limit from 0 to 3 plus minus 96 into 10 to the power 6x 4 divided by 4, limit from 0 to 3. Okay. So when you solve this, you will get 1777 joules, or that is equal to 1.78 kilojoule. So this is the amount of bending, this is the amount of strain energy that will be stored in the beam due to bending. Now what we will do is that we will find the axial strain energy. Axial strain energy. Let me write it here. This is bending strain energy. Okay. For axial strain energy, we know that strain energy due to axial loading is equal to integral of 0 to L n square dx divided by 2 AE. Clear? So what we will do is that we have n. N is actually the normal load or axial load. So you can see the axial load of this post is PS, 12 kilonewton. This beam is applied 12 kilonewton load on this post. So I will write from 0 to L 12 kilonewton. So 12, and that is also equal to, since it is equal to n square L divided by 2 AE. Okay. So 12 into 10 to the power 3 whole square. I will remove these things because this is already, we know that axial strain energy is equal to normal load square into L divided by 2 AE. So if you write this or this, both will give you the same thing. And length of each post is 1.5 meter. So 1.5 divided by 2 times area. Area of this cross section is given. So area is 0.05 multiplied by 0.05. And E is 70 gigapascal, 70 to 10 to the power 9. That is due to axial loading. So when you calculate it, you will get strain energy due to axial loading will comes out to be 0.617 joule. So this is the amount of strain energy that will be stored in each of the post. Clear? And that was all about this problem 14-22. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning, as well as help me in growing my channel further. Thank you for watching and thank you for your support. Welcome back. In this video, we are going to solve problem 14-32 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the slope at point A of the beam. EI is constant. So you can see this is the beam having a roller support at point B and there is a pin support at point C. And at point A, there is external movement M naught. Clear? So due to this movement, there will be bending stress. So you have to find the slope of point A. And due to this movement, this beam will bend like this. So this will be the slope of point A. So let's start with the solution. So what we will use is we will use conservation of energy, which is that strain energy due to external movement is equal to strain energy due to bending. So due to this movement M naught, the external strain energy will be equal to 1 over 2 M naught into theta A, and theta A will be the slope of that point A. Let's say this beam will bend like this. So this will be the theta A. So you have to find theta A, and this will be the strain energy due to bending. Now what we will do is that for strain energy in bending, we will first find this. How you will find this? So we will do is that first we will find this reaction forces. If you remove this roller support at point B, so you will be having a vertical reaction force which will be RB, and there will be a vertical reaction in downward direction at point C, and this will be RC. So we will find this RB and RC by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point B is equal to 0 taking the counterclockwise moment as positive. So about point B, the first moment is m naught, which is counterclockwise, so it will be plus. So I will write m naught. The second moment due to point B due to RC will be RC into perpendicular distance A, and that will be clockwise, so it will be negative. So I will write minus RC multiplied by A is equal to 0. So from here we will get RC will be equal to m naught divided by A. So this is the reaction force that this pin supports upper on beam. Now we'll find this RB by using sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see RB is upward minus RC, which is m naught by A, and that their sum must be equal to 0. So from here RB will be also equal to m naught divided by A. So both values are positive, so it means that our assumed direction, that RB is upward and RC is downward, is correct. Now the next step is that we have this reaction force. So what we will do is that we will cut the beam between A and B for region AB. So it means that X is greater than 0 and less than A. So this will be your X. So if I draw the free body diagram of this beam, so it will be like this. So at this is point A, where you have only external moment m naught, and this is distance x. So if you cut it, you will be having a shear force and you will be having a moment m. Clear? So how we'll find this? So we'll find this by using sum of all forces. Let this is your point 1. Sum of all forces about moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So you can see m naught, which is counterclockwise, and m is also counterclockwise, is their sum must be equal to 0. It means that reaction force is equal to minus m naught. So what does it mean? It means that our assumed direction, that this movement is counterclockwise, is wrong. It should be in clockwise direction. Next step is that we will do is for region C onward. And again, what we will do is that is you cut the beam, this will be your x, that this is your x1. Clear? So this will be x1, and this will be for region x2. So what we will do is that when you cut the beam over here, so this is the beam and this is x2. So you can see when you cut it, you will be having a shear force and you will be having a moment. That this is point 2. So how you will find this external moment? By using sum of all moment about point 2 is equal to 0, and taking the counterclockwise moment as positive. So m, which is clockwise, so minus m, there is no other moment, is equal to 0. So it means that this moment is equal to 0 for the region x2 is, I will write x2 is greater than or equal to 0 and less or equal to A. Now the third step is that if you cut this beam at this point, clear, and let this is x3 start from C, this is x3. So for region CB, x3 is greater than or equal to 0 and less or equal to A. So when you cut this and draw the free body diagram of the beam, so it will be like this. This is your point C, where you have RC, and RC value is m naught by A, and this is distance x3. So when you cut it, you will be having a shear force and you will be having a moment. Let this is your point 3. So we are going to find out this moment by using sum of all moment about point 3 is equal to 0, and taking the counterclockwise moment as positive. So about point 3, one moment is this m, which is clockwise, and this will be minus m. So minus m, and the second moment about point 3 is due to this m naught into A, and perpendicular distance is x3, and this is this is also clockwise. So minus m naught over A into 3 is equal to x3, not 3. X3 is equal to 0. So it means that this moment m is equal to minus m naught x3 over A. Clear? And this sign negatives mean that our assumed direction is wrong, so it should be in counterclockwise direction. Now we have all three moments for the region. So what we will do is that we will get this ui strain energy due to bending, and this strain energy due to bending, we know that this is equal to, for whole beam 0 to L, this is the general equation, m square dx over 2 ei. For three region, I will divide it as ei is constant, so I will take ei outside, and we will have integral from 0 to A minus m naught in m naught square into dx1. This is for region AB, plus again integral from 0 to A, and for second one we have this minus m, which is 0. So 0 square into dx2, plus integral from 0 to A, and the third one was this one, minus m naught x3 divided by A whole square dx3, and we will close the square bracket. So from here ui strain energy due to bending is equal to 1 over 2 ei, and this will give you minus m naught square x, and limit will be from 0 to A. Clear? Plus this will give you 0, and this will give you minus m naught plus m naught square over A square into x3 square. So integral of x3 square will be x3 cube divided by 3, and limit from 0 to A. Clear? And if you further simplify it, 1 over 2 ei into this will be also plus, this will be m naught square A plus 0 plus m naught square over 3a into a cube. Okay, this is a square. That will give you strain energy due to bending. So 1 over 2 ei into m naught square a plus m naught square a over 3. Clear? And if you take the LCM, that will give you 3 and there is 1 over here. So 3 is divided by 1 is 3. So 3 m naught square a plus m naught square a. Clear? And that will give you 4 m naught square a over 3 multiplied by 1 over 2 e I. So that will give you 2 m naught square a over 3. That will be the strain energy due to bending. Now we will use this equation, conservation of energy. So I will write 1 over 2 m naught into theta a is equal to 2 m naught square a over 3. Because we have said that strain energy due to external work is equal to strain energy due to bending. Clear? So from here, this theta a, which is slope at point A, will be equal to 4 times m naught a over 3 e I. Why? Because there is a 3 e I as well. Clear? So here 3 e I. And you can see this is the answer of our this question. And that was all about this problem 14-32. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-88 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. And the topic which we are covering is stress concentration. So statement is, if allowable normal stress for the bar is 120 megapascal, determine the maximum axial force P that can be applied. So you can see this is the bar that is subjected to axial load P, and the allowable stress for that bar is 120 megapascal. So you have to determine this P load. Now you can see from in this figure we have fillet as well as hole in this bar. So what we are going to do is we will find the P for fillet as well as for the hole. So let's start with the solution. So we know that maximum stress or allowable stress both are same. This is equal to stress concentration factor multiplied by sigma average. So what we are going to do is that for fillet we will find the stress concentration factor. So I will write for fillet we will find K. Clear? How we'll find K? You can see this graph that is available in chapter number 4. So I have taken that from that portion. So for finding K, we need R by H and W by H. So what will be W by H? I will write W by H and R by H. So you can see W here is this one. So R is this one, which is fillet radius. Height is the H is the minimum height of this portion, and T is the thickness. Clear? So here what we are going to do is that we will find W by H. So W is 40 and H is 20. So 40 divided by 20, which will give us 2. And now we'll find R by H. So radius of fillet is 10. So I will write 10 divided by H is 20 millimeter. So 20, which gives you 0.5. Now W by H is 2 and R by H is 0.5. So using this figure, you can see this is 0.5. If I draw vertical line, so you can see it will cross this W by H is 2, which is this graph. You can see this graph, and that is intersecting over here. So if you take a horizontal line, that will intersect y-axis, and K will be 1.4. So what I will write it over here. K is 1.4. K is equal to 1.4. Now what we will do is that we will find the average stress due to this load. So we know that average stress is equal to P divided by A. P is not known, and for this portion you can see this will be the cross-sectional area. So height is 20 millimeter and thickness is 5 millimeter. So we will convert it into meter. So area will be equal to 0.02 multiplied by 0.005. Clear? And we also have allowable stress, which is 120 megapascal. So you have both three values. So put it, allowable stress is equal to K into average stress. So 120 into 10 to the power 6 Pascal will be equal to 1.4 multiplied by average stress is P divided by 0.02 into 0.005. Clear? As we are interested to find out P, so P will be equal to 120 into 10 to the power 6 multiplied by 0.02 multiplied by 0.005 divided by 1.4. So when you calculate it, you will get P will be equal to 8.57 kilonewton. Now this load P is due to this fillet. We'll now move towards for finding hole. So for hole, again, we have maximum stress or allowable stress is equal to K into sigma average. So we'll first find this K. How you will find this K? So by using this graph, because this bar contain hole. So for that we will need this 2R by H. So 2R by W. So what is 2R? 2R is this diameter of hole, which is 20 millimeter, and W is 40 millimeter, which is this height of maximum bar. So I will write 20 divided by 40, and that will give you 0.5. Now you can see that 0.5 is this point. If I draw vertical line, it is intersecting this graph at this point. And if you take a horizontal line from this, so this will be your 2.1 will be your K. So K is equal to 2.1. Allowable stress is already given, which is equal to 120 megapascal. So 120 into 10 to the power 6 Pascal. So we will find sigma average. So we know that sigma average is equal to load per unit area. So load which we are calculating, or we want to calculate, divided by the area. So you can see this bar contain hole. So what will be the cross-sectional area? So this cross-sectional area will be this W minus this hole into this thickness will give you this cross-sectional area. So W is 40 and thickness is 5 and diameter of hole is 20. So I will write 0.04 minus the diameter of hole, which is 0.02 into thickness 0.005. So you can see you have value of K, allowable stress and average stress. So just put it in this formula that allowable stress is equal to stress concentration factor into sigma average. So 120 into 10 to the power 6 is equal to 2.1 multiplied by P divided by 0.04 minus 0.02 into 0.005. Clear? And from here you will get P will be equal to 120 into 10 to the power 6 multiplied by 0.04 minus 0.02 multiplied by 0.005 divided by 2.1. So what we will get is that P will be equal to 5.71 kilonewton. Now this is the P load applied, or allowable P load that can be applied to hole. Now we have two values. One is this and another one is this. So we will choose the smallest value. Why we will choose the smallest value is 5.71 kilonewton, and the reason why we choose the smallest value is because it will be safer and that can be applied. So if you apply this force that exceed the allowable stress in this bar, and this will fail. And that was all about this problem 4-88. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning as well. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-94 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the resulting stress distribution along section AB for the bar is shown. From this distribution, determine the approximate resultant axial force P applied to the bar. Also, what is the stress concentration factor for this geometry? So you can see this is a bar having fillet, clear, and at section AB, the stress distribution is shown like that, clear, and there is a P load applied to this bar. So you can see the highest intensity is 12 ksi, and the intensity of each of this segment is 3 ksi. So there are 4 segments, and if we count it, so there are 1 2 3 4 5 6 7 8 9 and 10 approximately square bar. The thickness of this bar is 0.5 inch. So let's start with the solution. So as we know that this P load is equal to integral of stress into dA. So what does it mean? It means that volume under curve. So where is the curve? So you can see this is the curve, clear? So volume of this curve will be like this one. Okay, so how we'll find this? So let's start solving this problem. So as we know that I have already discussed that number of square in this volume is equal to 10. Let me count it again. So you can see 1 square, 2 and 3 plus 4, 5, 6, 7, 8, 9 and 10. So approximately there are 10 square. So we know that P will be equal to, you can see the intensity of 1 is 3, one of the square side is 3 ksi. So 3 multiplied by the area. What is the area? So 1 is the height of this and 0.5 is the thickness. So 3 into 1 into 0.5. So there are 10 squares, so I will multiply it with 10. So it will give you the P load, which is the volume under the curve. And when you calculate it, it will be equal to 15 kips. So I will write P will be equal to 15 kips, which is the answer of our first part. Clear? Now we'll find the stress concentration factor. I will write it, stress concentration factor, K. So we know that due to this fillet, there will be a maximum stress at this fillet portion, clear, and minimum stress will be at the middle. So what we will going to do is that we will find this stress concentration factor. So we know that this maximum stress will be equal to stress concentration factor into sigma average. So how you will find sigma average? So sigma average is equal to P divided by A. Now, what is P? So P is 15 kips. So 15 kip multiplied by what is the area of this portion? So this is thickness 0.5 and total height is 4 inch. So this will be the cross-sectional area over which this P act. So P divided by 4 inch multiplied by 0.5 inch. And when you calculate it, it will be 7.5 KSI. Okay. So from here, sigma average is equal to 7.5 KSI. So what we are going to do is that we will find this K. Clear? So how we'll find this K? You will need average maximum stress. So maximum stress can be taken from curve, and that maximum stress is 12 KSI. So sigma max is equal to 12 KSI. So we know that maximum stress is equal to K into sigma average. So from here, this K will be equal to sigma max divided by sigma average. So put the value, sigma max is 12 KSI and sigma average is 7.5 KSI, which will give you 1.60. So the stress concentration factor is 1.60 required stress concentration factor for this bar, which is the answer of our this question. And that was all about this problem 4-94. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help them in learning process. And I am very thankful to you people for supporting me throughout my this journey on YouTube channel. Thank you.